recording and we'll get started today. I'm assuming everyone can see the orange screen on there. If you're not seeing my orange PowerPoint slide, do send me a message. Send something in via the Q&A box. Let me know that it's not streaming the screen right, but it should be shared, but I'm not seeing the normal indicator that's telling me the screen's shared. Anyway, so we'll get started. So for those of you that are new to Zyxel, we're signing up new partners every day. Just a single slide here to talk a little bit about who we are. We fully recognize we are not a household name. Many of you have never heard of us until somebody at distribution or you run into us at a trade show. So just a little background on who we are. We've been building networking equipment since 1989. We were one of the pioneers in the early days of analog modems, specifically those modems used by bulletin boards and dial-up service providers back in the day, back when you still dialed in. So that's where we got our start. We moved from there into DSL modems, cable modems, things like that. So we've got a little over 100 million devices deployed out in the field. We do have offices in most major countries. We've got a little over 1,500 employees, and we're serving 150 different global markets. The US office is based out of Anaheim. So that's our sales, that's our warehouse, and that's also our tech support. So when you call in and talk to somebody from tech support, you are talking to an actual Zyxel employee sitting here in Anaheim. Although if we can get them figured out here, pretty soon they'll be working from home. But in general, just wanted to let you know that when you call in, you are dealing with a Zyxel employee. It's not an outsourced call center you're dealing with. It's not somebody overseas in the Philippines or India. You are talking to us here. So let's get started. So we'll start here by talking about some of the names you'll see out there thrown around a lot. So one of the most common ones you're going to get is IEEE. Ooh, my phone just shut off. So IEEE is an industry organization. The main thing that we're concerned is how these set the standards for a lot of networking, right? So when you look at a data sheet and you look at what the Ethernet ports are, you'll see a bunch of IEEE 802, 801, 80 something numbers talking about standards on a lot of different networking equipment, including Wi-Fi. So Wi-Fi is 802.11. So they're the ones who get together. It's a large international organization of engineers, and they build the standards that then everyone uses to make their hardware off of. The Wi-Fi Alliance is primarily a group of manufacturers. So the Wi-Fi Alliance manufacturers get together, and it's more of a marketing arm. So they're the ones that came up with the idea of naming IEEE 802.11 as Wi-Fi. They're also the ones behind recently renaming 802.11 AX as Wi-Fi 6, 802.11 AC as Wi-Fi 5, etc. They also certify compatibility. So if you see something that's got Wi-Fi certified, it has passed some compatibility testing that's been done to make sure everybody plays nicely with each other. You do not have to be Wi-Fi certified, and in fact, most business class products do not bother to be Wi-Fi certified, where most consumer products do. And then we've also got the good old FCC here in the US. Industry Canada, if you're up in Canada, every country has their own group. And these are the guys who set the rules as far as power output, which frequencies can be used, other sorts of behaviors and things like that. So FCC sets the rules, not always so good at enforcing the rules. So here at Zyxel, we try our best to comply with the rules. There have been some other players out there that do not. Famously, a few years back, Netgear sued, I believe it was ASUS, because ASUS was shipping in product that exceeded, if I'm remembering this correctly, that exceeded power limits for the channels being used. So they were getting great reviews on sites like Small Net Builder and whatnot because the performance was great, but the performance was great because they were in violation of the rules. And Netgear ended up having to sue to get those rules enforced. So let's start talking about Wi-Fi here, technical perspective. So Wi-Fi works using radio waves, right? So very similar to what your TV radio waves, radio station radio waves. It's all the same thing. It's just different chunks of spectrum that have been, narrowed out for certain uses. So satellite TV, if you're doing satellite TV, those satellites are using certain radio frequencies to send the TV signal down. So just as a general rule here, as frequency goes up, you can force more data. It's easy to put more data on there. but also as the frequency goes up, the range becomes less. So those of you that are old like me, you probably remember the old original cordless phones that were in the 900 megahertz spectrum. They had the big old silver collapsible antenna. So those were really great when those first came out because you could get on a phone, especially if you were a kid at the time, and you could walk outside, walk partway down the block, maybe even if you were lucky, go over to your friend's house and still maintain a phone conversation. The late 80s, early 90s, there was a move to go from 900 megahertz to 2.4 gigahertz. So we've increased the frequency significantly. Sound quality got a lot better. That was one of the main pitches behind it. But the range became less. So, you know, by going to 2.4, now you can no longer walk over to your friend's house. If you were lucky, you could go outside and, you know, still stay on the phone if you were out in your yard. And then in the early to mid 90s, we saw a move on cordless phones to the 5 gigahertz spectrum. This was primarily done because 2.4, as we'll get to later, is kind of a small area of bandwidth. And what am I going to say here? So 5 gigahertz opens up a lot more, although most of these phones were pitched again on the idea that the sound quality was better. Why? Frequency went up. You could fit more voice data on there easily. So sound quality improved, but the range got even less. So maybe now with these 5 gigahertz phones, you can't go outside anymore. And if you've got a big McMansion, maybe there's certain rooms in the house that didn't work so well when talking on the phone. Hold on just a second. Oh, that's not working. So anyway, frequencies are regulated by the FCC. In order to broadcast on most channels, you need to have a license from the FCC. So what the FCC did, though, is they opened up some small areas of spectrum that everybody can use. And you'll notice these are the same frequencies that cordless phones went through. We have 900 megahertz here to 928 megahertz. That was your original 900. 2.4 to 2.483 is your 2.4 gigahertz spectrum. 5.15 to 5.825 is your 5 gigahertz spectrum. So Wi-Fi works on these bottom two. There have been some other wireless communication technologies in 900, but just in general, because the frequency is so low, you just can't get enough data on there historically to make 900 worthwhile for wireless data communication. So when you're looking at specs, one of the things you're going to see here is power output. So you will see it done one of two ways. Generally, when you're looking at consumer equipment, you will see stuff advertised as milliwatt output power. Milliwatts are also can be used, and you'll find this more in your business class products. Power output will be measured in dBm. So same thing, just different ways of denoting it. So generally in the business stuff, dBm is what you will see. So you can see here we've got some comparisons of what the dBm converts into. So one of the things to note here is if you add 3 dB, so we go from 20 to 23, you've doubled your power output in milliwatt. And that holds true throughout the entire dBm range. So again here, you see here we go from 30, we add 6. So we double 1,000 to 2,000 and double it again to get 4,000 or 4 watts of output power. The nice thing about using dBm is you can add in your antenna gain, your dBi, add these together and get the total output power. So it makes it really easy to do calculations there. If you're using any sort of link rate calculator where you're trying to determine what sort of distance you can get on a Wi-Fi link, you'll be using dBm and dBi to do that. And also, milliwatt is really misleading when it comes to range, right? You've doubled your range, right? You go from 100 milliwatts to 200, you've doubled your coverage area. No, you haven't. You've increased your range, but not by anywhere near doubling it. You know, 20 to 23 is probably a much better idea of the sort of range increase you're going to get than 100 to 200. So another thing to talk about here is signal to noise ratio. And this is something people tend to overlook a lot, even though it's probably the most important thing when it comes to Wi-Fi communication. So when you're dealing with things here, you have the signal, right? The signal that either your access point is sending or your phone or whatever is sending back to the access point. But you also have RF noise. So it's the ratio of signal strength versus this other noise that's operating on the same 2.4 gigahertz or 5 gigahertz channel that you're trying to use that really determines the quality of your signal. So even if the signal is weak, if you've got good signal to noise ratio, you should be able to maintain a connection really well. You might have a really strong signal, but because of other sources of RF interference, other access points, other wireless devices, industrial equipment, strong signal does you no good if the noise floor is just as strong as that and your device cannot make out the the signal it wants to hear versus the noise. So an analogy here would be, right, so if you and I are sitting in an empty conference room at a table across from each other, we can talk with normal voices. We can hear each other. The signal is high, and because we're in this empty conference room, there's really no noise. So there's a really high signal to noise ratio. You might hear a little bit of the air conditioner humming or people walking by outside, but in general, there's very little noise that you have to differentiate between what the person you're talking to is talking about. So now we take that same scenario, same distance apart, but instead of being in a conference room, it's 1 a.m. and we're at a nightclub sitting across from each other at a small table. Now, if we both talk at the same volume level as we were before in the conference room, we're not going to be able to make out what each other is saying, right? You have to get closer together. You have to shout into each other's ears to be able to be heard over the noise of the music and everybody else that's in that nightclub. So it's the same thing with Wi-Fi. That other noise in the nightclub, whether it's music, other people talking, that's your noise floor. The person you're trying to communicate with, that's your signal. And because there's very little difference between the volume of the signal to the noise, it's really hard to hold a conversation without increasing the signal or getting closer together. So the other thing to talk about is attenuation. So attenuation is basically a fancy word to talk about how much the signal decreases as it travels distances and as it penetrates through objects, people, cubicle walls, things like that. So again, 2.4, much less attenuation over distance, generally much less attenuation penetrating objects versus 5 gigahertz. Because again, as frequency goes up, range goes down. So if you want to go, well, Sean, tell me this access point, how far is it going to cover? What's the coverage area? Right up here at the top of your screen, that's the formula you need to know to be able to figure this out. And that's assuming no noise floor. So 20 log 10 of your distance, 20 log 10 of your frequency, add 92.45 up there, and that tells you your free space path loss. Then you got to figure out what your noise floor is. So as you can see, it gets really complicated really quick. So that's why we generally don't give any sort of ranges. There's so much going on in the environment that's going to affect how far you can have the communication, what your range is on that access point. There's also something else really important that we'll talk about in one of the upcoming slides here. There we go. As you can see here, window give you a 3 dB loss. So it halves your power, drops your effective range down to 70%. If you've got a tinted window, it's got one of those metal coatings that keeps out UV or infrared. That can double or triple how much loss you're going to experience. And then obviously as you go up into thicker and thicker walls and floors, the more data loss you're going to, or attenuation you're going to have. So the other thing to keep in mind when people talk about range, right, is that Wi-Fi is two-way communication, and people tend to forget this. So your range is generally going to be determined by the weakest member. So, here's a traditional access point. It's got 500 milliwatts of output power, which actually is kind of low these days. It can send its signal really far. The problem is it's talking to your cell phone, it's talking to your tablet, and it has a lot less power output. iPhone traditionally has around 25 milliwatts of output power. 500 milliwatts here, 25 going back. So the access point can shout all the way down here, and your phone can hear it just fine. But the access point can't hear your phone whispering back. So that's something also to keep in mind. This comes into problems what we run into where people have got their APs maximum power. That AP signal can be seen all throughout the building, but you have to add additional access points throughout the building because the phone or tablet or whatever can't get the signal back to that one AP. So you add additional access points around. all of them have this huge output power on the signal. And what happens is they end up interfering with each other. Another thing here, just to explain, this is something that happens a lot, where people will look at their phone or their signal strength in their laptop and say, hey, I've got a perfectly good signal. I've got 3 out of 5 bars. I've got 4 out of 5 bars. Why does this connection suck? And it's because your device is telling you how strong the signal is coming from the access point to the phone. It doesn't know how strong the signal is at the access point coming back from the phone. So what's happening is this point sends the data and then says, can you confirm you received the data? Here's the checksum. The phone says, yeah, I received it, but the access point never hears. So it ends up just keeps asking, hey, have you got that data yet? I'm not going to send you more data until you confirm that you've received what I sent you already. So that's why you run into that problem a lot. So when it comes to RF behavior, if we're trying to visualize how it behaves in the real world, a good thing to look at or to visualize is just a pond. So if you've got a pond, maybe you've got a little dock that goes out into the pond, you throw a rock into the pond, and then watch the ripples radiate out from it. Very similar to what happens with your access point or your laptop when it sends the signal. It's basically those ripples are your radio waves, and they behave very similar to water waves. So if you've got an object in the way, it'll weaken the strength. And I mean, one thing that radio waves can do that water can is it can pass through a physical obstruction. It may bounce off of things and reflect. We've seen that before, right? Waves hit like a concrete wall in the pond or whatever, and they'll bounce back out. It can scatter and break up into multiple smaller waves, and it can actually sort of wrap around physical stuff. We've probably all seen that before. Again, going back to the idea of a pond. You've got a little dock out there. You've got little pillars that come down. The wave hits those pillars, and the wave sort of wraps around them. Same thing happens with Wi-Fi. So another important thing to talk about here is when we're talking about radio wave communication, only one device, with one big exception, can transmit at a time. And we'll talk about the exception later. But in general, everybody takes turns broadcasting. Access point sends some data, client sends some data, a different client sends some data, the access point sends more data. What happens is if 2 or more devices decide to transmit at the same time, it causes interference, and one or both of them will have their communication dropped. If you remember the old days of walkie-talkies, I'm not sure this happens as much on the digital walkie-talkies, but certainly on the old analog walkie-talkies I had as a kid, you know, if 2 of your friends tried to talk at the same time, you would just get a horrible, nasty noise coming through your walkie-talkie. Same thing with Wi-Fi. It's radio wave is just the same, causes the same sort of interference. Now, back when 802.11 first came out, they go, well, how do we deal with that? And the answer was pretty straightforward. Basically, when your device wants to transmit some data, it listens first and says, hey, is anybody else sending data? If someone is, then we go to a random number generator and our device waits that random amount of time and then checks again. If it listens and no one is transmitting, it will then transmit its data. So one of the problems you run into a lot is, especially if you have a lot of client devices, multiple devices will be wanting to send data. Both will detect, hey, wait a minute, nobody's using the radio right now. I can go ahead and send, and then you end up with multiple devices transmitting data, which causes a collision. So then they have to wait and then try again to retransmit that data. Going along with that, we run into this problem here. It's called a hidden node problem. And what happens is, we've got our access point here in the middle. Look at that old slide. Remember those guys? The old B2000, B3000? You've got your laptop over here. You've got your laptop over here. Both are within the coverage area of your access point. The access point can receive communication from both devices, no problem. The problem you run into is each individual device, it has enough range to be able to see and hear what's going on at the access point, but its signal isn't able to see that there's another device over here. So what happens here in this hidden node problem is neither device knows the other device is transmitting. So they always assume, hey, there's free time, I can transmit. And what ends up happening is your access point receives the communication from both at the same time, the signals interfere, your packets are dropped. So another thing I want to talk about here has to do with what I'm going to call data rate versus throughput. I'm not necessarily using these terms correctly. These terms oftentimes are interchangeable depending on how they're being used, but I am using these in the way that you most often see these brought up, especially if you're looking at something like Amazon reviews and things like that. So there's a lot of confusion here. So when it comes to networking equipment, it doesn't matter whether it's an Ethernet switch, power line technology, MoCA technology, or Wi-Fi technology, the product speed is advertised as a matter of the data rate. So the data rate measures how much communication there is between the two devices. So between your computer and the switch, or between your computer and the access point. So this terminology can also be referenced as a physical rate or the link rate. Now the key thing here is, in addition to the data you want to send, say you want to send a file to somebody that's 5 megs, it includes that 5 megs in the data rate, but it also includes all the device protocol overheads, TCP overheads, in the case of Wi-Fi, all the 802.11 overhead that makes 802.11 possible. So there's lots of error checking and retransmits and all sorts of other stuff to ensure the integrity of the data being sent out over this 2.4 or 5 gigahertz spectrum, which is shared by a lot of other devices. So in the old days of Ethernet, right, there's very little protocol overhead for the actual physical medium of Ethernet. There's a little TCP overhead and some packet overhead, but not a lot. So what happens is the data that you want to send, your file, is the bulk of the bandwidth that's available over that connection. With Wi-Fi, it's very different. So you've got your data, but your data is only a small subsegment of the total data that's being sent between the devices. So you've got all this other protocol overhead and transmits and stuff. So what happens is the throughput that people measure with something like speedtest.net or iPerf is only looking at the data being sent, the file that's being sent, and not the actual protocol or the total information that's being sent. So we'll normally call that throughput. And what they'll see is, hey, wait a minute, I bought a 300 megabit per second wireless device. Why am I only getting 112 megs throughput? And so that's what it is people are measuring this, how long it takes to transmit this 5 meg file, and they're not measuring all this other data that's being sent between the wireless devices, all this protocol overhead. So with an Ethernet switch, maybe you've only got 1% overhead. With Wi-Fi, you've easily got 60% overhead. So you have to take in that into account. Then you have to throw in how far you are from the access point, spatial streams, all this other stuff, which is why people will see a lot lower throughput as measured with something like speedtest.net versus the data rate, which you'll see on the data sheet in the product listing. So that leads up to, well, how do we increase speed? So this is not how you would increase speed, but this is how the Wi-Fi technology in general, how do we increase the speed? So there's a couple ways of doing it. One thing we do here is we have our encoding. How much data are we encoding onto those radio waves? So 802.11 used what's called 64-bit QAM. 11AC increased the encoding to 256 bits. And now Wi-Fi 6 has increased it to over 1,000 bits of data. So you go, well, why didn't we do that sooner? And, there's two reasons. One, we just didn't have the horsepower to do it, right? To take this data and encode it onto the radio waves requires a lot of horsepower. It also requires a lot more sensitivity to make sure you can see that data and break it apart. And then on top of that, because Wi-Fi is mobile, even if we had the horsepower, you need not just the horsepower, but also the efficiency of that horsepower. So you're not eating into somebody's battery time to be able to achieve that. We have what are called spatial streams. And we'll talk about what those are here in a little bit. And then the other way to do it is increasing bandwidth. 11G went from 20 megahertz, 11N added 40 megahertz. So the amount of bandwidth you're using at one time doubled. 11AC gave you up to 80 megahertz or 160 megahertz, depending on whether you're looking at wave 1 or wave 2. So we'll start talking about here first, we'll talk about the 2.4 gigahertz spectrum. So in the United States, we're only allowed to use channels 1 through 11, which is great, right? We've got 11 different channels that we can use. so we don't have to worry about interference. Wrong. Basically, this segment here that we are allowed to use, and there's a little bit of overlap over here, is about 60 megahertz total bandwidth. A Wi-Fi channel, again, is around 20 megahertz, right? So what that means is, well, we've got, 11 channels you can choose in the drop-down menu. They actually overlap with each other, right? You can see these little dotted lines here showing how each channel overlaps. So in America, with using 20 megahertz channels, we've only got 3 that can be used, right? Because we've only got about 60 megahertz of bandwidth total available for us to use. Each channel is around 20 megahertz, so therefore you've only got 3 before you cause interference. So you might remember on the previous slide, we mentioned one of the ways you increase speed was you increase the bandwidth used. So 11N and some of the pre-N products, their big selling point was we've doubled the speed, and they did that by using a 40 megahertz channel instead of a 20 megahertz channel. So what does that do for us? Again, we've only got 60 megahertz approximately available in this 2.4 spectrum. So if you try to use 2 devices using this 40 megahertz spectrum, what happens? They overlap and interfere with each other. So now you've gone from 3 channels that can be used without causing interference to only 1 channel. So as soon as you have a neighbor that's also using 2.4 and 40 megahertz channels, you have interference. As soon as you have another access point in your office, you've got interference on your 2.4 channel. So what happens is, well, everyone advertised 40 megahertz channels and double the speed. Realistically, very few people could actually take advantage of the 40 megahertz channel in the 2.4 space. So that's why you saw a big push with 11N to using 5 gigahertz channels. So why do we want to use 5 gigahertz channels? 5 gigahertz is a much, much larger chunk of spectrum here. I forget the exact number here, but you've got around, I think it's like 25, 26, 20 megahertz channels that don't interfere with each other, right? So now you can have a lot of access points, a lot of neighbors. Each one of you gets your own 20 megahertz spectrum that you can use without worrying about interference. You can have a lot of access points in your office, no interference. So that's why we saw the push to 5 gigahertz. Even though 5 gigahertz doesn't travel as far, right? The range is less, so you need more access points. Although realistically, again, because of the huge difference in power between an access point and a client device, it's not as big of a deal as it maybe seems at first. But you'll also notice here on my chart, I've got all this stuff highlighted here. So what's going on here with these orange channels? So these are what we call DFS channels. So basically, when the FCC came along and said, hey, you know what? We're going to let you guys use this chunk of spectrum, but there's a problem. Someone else is already using that. This chunk of spectrum is what's being used by radar. Could be military radar, could be airport radar, or in this little chunk here, it's dedicated to weather radar. So you can use this channel, but there's some rules when it comes to using it. So what you have to do is before you transmit and start using this channel, you have to listen. And I think it's either 30 seconds or 60 seconds. You have to stop and listen and make sure there's no radar nearby. There's no airports nearby, et cetera, using those channels. And then you can use them. But you also have to constantly monitor that channel. And if you detect suddenly that there's radar on that channel, you must instantly stop broadcasting on that channel. And generally what happens is the access point will then switch to another channel. But again, if that is a DFS channel that it switches to, it's going to have to wait 30 seconds or a minute before it can start working. So if you were a user and you're connected to that channel, you're now disconnected for 30 seconds or so every time it detects radar on the channel you're currently using. So if you happen to be someplace near a major metropolitan area where there's probably lots of different radars being used at airports and things like that, you may experience frequent disconnections. The other problem that goes into that is in order to be certified to support DFS, it adds up to 6 months to the FCC certification process. And especially on the consumer side of things, where there's this huge war to be the first guy to market with any new technology, what happens is a lot of the consumer grade equipment never bothers to go through this DFS. They just want to get out into the market as soon as possible, and they never bother spending the money or putting out a firmware update to add the DFS support. So what we run into a lot is if businesses, people will call our tech support and they'll go, hey, you know, we've got this problem here. Bob's got, you know, he's got this tablet he bought, he's bringing to the office to use, and Bob can't connect to your network. What's wrong with your guys' access points? Why aren't you compatible with Bob's tablet? And the answer to that generally has been, you're using DFS channels. Bob's tablet doesn't support DFS channels, so that's why Bob can't connect. His hardware legally cannot connect to those DFS channels. So for that reason, a lot of people choose to never use these DFS channels. They don't want to deal with people's bring your own device not being compatible. They don't want to deal with randomly people being kicked off the network, even if it's only for 30 seconds or so, because the access point detects possible radar usage on the same channel. So you'll notice here we go from what, 25 or 26 on the 20 megahertz channels to only 9 non-overlapping channels. But then again, I said, right, one of the ways you increase speed is you increase the bandwidth being used. So if you switch to 40 megahertz channels, doubling your throughput, now you've only got 4 non-overlapping channels that you can use without using the DFS channels. 11AC lets us use 80 megahertz channels, doubling the speed again over the 40 megahertz channels. So now if we don't want to touch DFS channels, we've only got 2 that can be used before there's interference. So if it's just you and one access point, you're good. Your neighbor has an access point, it's good. Your other neighbor on the other side, they throw in their access point, they're now going to be interfering with one of these 2 channels that you're using. That's very important here to keep that in mind. And then again, with 11AC V2 and some of the Wi-Fi 6, we're now up to 160 megahertz channels, doubling the performance. But again, now with 160 megahertz, there's no chunk of non-DFS channels that's 160 megahertz wide. So you absolutely have to use a DFS channel to use these 160 megahertz bandwidth. So now let's talk about spatial streams. You might remember before when I was talking about Wi-Fi behavior, that, you know, the signals go out and they bounce off of stuff. They refract, they scatter, they do things like that. So what happened is that causes issues, right? Historically, that caused issues. It's something that we call multipath, right? So the data comes out here, bounces off of this object, comes down here. Some of the signal goes straight to the device, some bounces off of this object, something goes down here and scatters. So what happens is you get what's essentially, in audio terms, echoes, right? We've all been in that, where you're in a, you know, weird shaped room that's all hard objects and you're talking to someone and you get a lot of echo and reverb going on. So it's the same thing here, and that reverb and echo effect is basically noise to the signal, right? So this is the signal you want to hear, the nice straight quick one. And then you've got all these echoes coming in because the signal is traveling a longer distance, hitting the object and bouncing off. And by doing that, it takes slightly longer time to get to your client device over here. So you end up with what's essentially sort of like echoes. You get scattering and some other stuff like that as well. So that is what we call multipath. So after a while, some people who are way smarter than me, some of them used to work at Zyxel's spinoff Zydas, which eventually we sold to Qualcomm, said, hey, you know what? We've got technology here that'll turn this multipath problem into a benefit. And basically what they did is they've got some smart technology here that allows you to basically takes advantage of the fact that we know these signals are coming in slightly offset time-wise because the signals are traveling slightly different paths. So what we say is, okay, here's what we can do. We can take advantage of that and some special technology on the chips, and it'll allow us to send data, different data, simultaneously using different paths. So one path of 100, so let's say the airtime utilization here only allows 150 megabits, right? So on a traditional access point, you would have a 150 megabit signal. getting to your client device. By taking advantage of multipath, using a technology called MIMO, multiple in, multiple out, we're able to send different data streams. So if we've got two antennas here that are capable of transmitting different spatial streams, one antenna sends 150 megabit signal, the other antenna sends a different 150 megabits, and those combine together to get you a 300 megabit signal. So if you saw an old N access point, those were, some of the cheap ones were N150, meaning these supported a 150 megabit stream, and you bought some others that were N300. That meant they had two different spatial streams that they could support and send data that way. If you bought an N450 product, that told you that there was three spatial streams capable of being sent at the same time. So even though they're using the same frequency, even though they're transmitting at the same time, because of some smart stuff going on here chip-wise when it comes to modulation, your client device is able to differentiate those signals and then combine them all together for a total aggregated throughput. Now with 11AC Wave 2, we added something here called MIMO, multiple user MIMO. And it works on 11AC downstream only, but it allows you to take those same two different data streams, and instead of sending that data to one device at 300 megabits, it lets you split them up and send 150 megabit spatial stream to one user and a different 150 megabit spatial stream to a different user. So oftentimes our access point here supports 3 spatial streams or 4 spatial streams, but your client devices only support 1 or 2 spatial streams. So that allows you to be able to then take advantage of that and send data to multiple client devices simultaneously. So that's called MIMO. So when you're looking at the data sheet for a business class access point, instead of seeing AC 1750 or N300 or whatever, you'll often see 2x2, 3x3, 2x3, etc. So what does that mean? So that's telling you how many spatial streams that can be supported. The first number, and my laptop is frozen up. Oh, that's not good. There we go. Is that working? Oh, partially working. So that tells us that the first one is how many transmit spatial streams. Second number is how many receive spatial streams. So generally on an access point, both numbers are going to be the same. If you can transmit 3 spatial streams, you can also receive 3 spatial streams, etc. However, on a lot of client devices, it's not so. A lot of client devices maybe will be a 2x1. They can receive 1x2. They can receive 2 spatial streams from your access point, but when they send data back to the access point, they can only use 1 spatial stream. And then if you look at Cisco stuff in particular, you'll often see them advertise a 4x4 or something like that, a colon, and then a 3, or a 3x3 colon 2. So with that, it's kind of misleading there. That number after the colon is how many spatial streams you actually can handle. And then the first numbers are how many essentially antennas you've got. So if you've got a 4x4 3, same amount of data as a 3x3, it just can choose from 4 different antennas which 3 it's going to use to listen on. So, in theory, it gives you just a little bit better because maybe one antenna doesn't have the best signal, the other antenna's got a slightly better signal, so you use the antenna with a slightly better signal. In real worlds, I've never seen much difference between that. So just keep that in mind. If you see a colon and then a number, that's your spatial streams, not the first numbers. So combine it all together here for you. This is just showing here, your spatial streams are here, your modulation type is here, your bandwidth is here, and that's how you get to your total maximum speed, right? So a 1x1 product, if you look at the speed ratings, you'll normally see 866.7 because we're taking best scenario, maximum QAM for the encryption or the encoding, maximum bandwidth. Again, we talked about here, almost no one's going to be using 160 megahertz. So right there, you're going to drop down to 433 is realistically the maximum most people are going to see. But again, if something happens, there's a lot of noise, you can't get to 256 QAM, well then it drops down to 325 at 64 QAM, etc. So another common question we get is, how many devices can I get on your access point? This access point says it supports 128. This access point supports 256. I'm buying the one that supports 256. Realistically, those numbers you see on data sheets mean bupkis. They serve no point whatsoever. Why? Because the Wi-Fi protocol itself is such a way, it works in such a way that you're going to hit the maximum number of clients you want to have on that access point long before you get to whatever's on the data sheet. You know, the data sheet measurement is basically how many MAC address entries and association entries it theoretically has the memory to support. But it doesn't matter whose access point it is, doesn't matter if it's an expensive one or a cheap one. In the real world, the limitation is the Wi-Fi protocol itself. So you're going to hit that Wi-Fi protocol real world limit long before you get anywhere near what's on the data sheet. Doesn't matter if it's our product or Cisco, you know, whether it's a $100 access point or a $2,000 one, it's the same. So we've given some real world examples here for you. So we've taken this scenario here. We've got an access point, and we've simulated clients at 67 dB signal strength, 5 gigahertz, 20 megahertz channels. So we take a bunch of laptops on there. Each laptop is trying to watch a 3 megabit stream. So what happens? We can support 34 laptops, right? The data sheet says we can support 256, but realistically, with the data time that's available, we can get to 34, and that'll get us 100 megs aggregated throughput across those laptops. So now we do the same simulation, but we switch to tablets, which in this theoretical example are only supporting 2 spatial streams. So the only thing that's changed is the number of spatial streams. So by going to devices that only support 2 spatial streams, now we can only fit 21 devices streaming that 3 megabit signal before you would have issues, for an aggregated 65 megabits total on that same access point. Again, we then take away 1 spatial stream and change it to a single spatial stream client device. Now we can only fit 10 on there for 30 megabits total aggregated throughput. And again, that's only looking at spatial streams. You know, in the real world, it gets really complicated because you've got people doing different types of data which have different demands. For instance, voice. If you're doing voice over Wi-Fi, this is something that, you know, drives VARs nuts trying to do this. And part of the reason for that is, while voice over Wi-Fi uses very little data, voice communication is two-way real time. There's no margin in there for buffering and for jitter, which is really common on Wi-Fi because of all the interference issues and hidden node problems that we've talked about earlier in today's slide deck. So because of that, voice over Wi-Fi is really hard to implement without getting complaints from your customers. So if you're doing voice over Wi-Fi, you may only want to have 16 devices per access point, even though in theory the bandwidth is there for hundreds and hundreds of devices because of the Wi-Fi protocol and the way the devices determine whether or not they get to transmit, right? So if you're doing voice, you can't pause and wait for the signal to free up. You can't risk 2 devices sending data at the same time, causing the packets to get dropped, because now packets are out of order and it turns into a garbled mess. So there's a lot of stuff going on in the real world. So in the real world, you're always going to hit the maximum number of devices for the type of device and the type of traffic and application long before you hit whatever numbers on the data sheet. So let's talk a little bit about co-channel interference. So co-channel interference is just the easy term to talk about multiple devices transmitting data at the same time on the same channel. It can be multiple access points. Remember 2.4 and 5 gigahertz, these are open spectrum that anybody can use. So any device that's doing wireless communication is probably using one or both channels, even if they're not technically using Wi-Fi. You know, microwaves put out 2.4 gigahertz interference. A lot of business class industrial equipment doesn't have to comply with FCC Class B guidelines, so they put out a lot of interference. It may be on the same channels your Wi-Fi is using, et cetera, et cetera. So there's lots of other sources of RF interference, which we called earlier the noise, right? RF noise, the noise floor, the difference between your signal to your noise. So traditionally, the way you dealt with this, right, with access points, is you spent a lot of time planning out where each access point is, and then trying to space them out, which channels they're using, so you don't have two APs next to each other operating on the same channel. But again, because of the difference in the power output on these access points, oftentimes that signal can jump 2 or 3 APs distance and still be causing interference on the same channel. So the way you dealt with that is you would try to turn down the power on the access point, and that absolutely reduces the amount of co-channel interference you have. Excuse me, the problem is it also worsens your signal to noise floor because now your signal is a lot less. So in a lot of times when that noise is not other access points, lowering your power made things worse or didn't make them any better at the very least. So traditionally your access point is something that you mount on the ceiling, those little round smoke detector or square ones. Those generally have what we call an umbrella pattern. So the antennas are covering a sort of circular area. If you've got a directional antenna on there, they focus the beams one way. So the Zyxel solution is to use smart antennas. So with smart antenna, we've got instead of having one fixed antenna pattern, we've got literally hundreds and hundreds of different antenna patterns we can use. And we're using an algorithm which will look, where is the client I'm talking to? And it will choose an antenna pattern that focuses the beam towards that client, boosting the signal strength. We also take into account sources of RF interference. So what happens there is we'll choose an antenna pattern both based on what optimizes the signal for the client, but also optimizes where we're listening on the received side of things to try to ignore other sources of RF interference. This technology is done entirely on the access point. Unlike beamforming and stuff like that, nothing needs to be done on the client. It will work with any vendor's client device, any type of client device, even devices that are moving and non-stationary. So here's a test situation we put together. We took our NWA 1302 wall mount hospitality AP, and we compared it to Ubiquity's UAP AC, what is it called? Let's see here, IW. Both have basically the same form factor, both have very similar RF performance and characteristics. The primary difference is whether or not we have a smart antenna. So we've done a situation here, think of this as an apartments or hospitality situation. You'll notice there are no overlapping access points directly next to each other, but even though you might have quite a bit of distance, that signal from the APs can still travel quite far and cause interference. So the first thing we did is we plugged in and turned on one access point and did some throughput testing. What you'll see here is we're both about the same speed. Ubiquity actually outperformed us slightly. A little over 400 megabits aggregated throughput across multiple clients. When it comes to airtime utilization, both are the same at 67%. So now we turn on a second AP on the channel. What happens? So you'll notice on ours, our aggregated throughput is 785 megabits per second. Whereas on Ubiquity, we've dropped down, we were only able to achieve 555 megabits aggregated throughput between those two APs. Why is that? And it has to do with the airtime, right? Every device has to take turns transmitting. In theory, no two devices are transmitting at the same time. So Ubiquity maxes out the available airtime, the time when devices can actually be transmitting data. They hit 95% achieve. You look at the Zyxel with smart antenna, and we are at 131% achieve. We are greater than the theoretical maximum airtime utilization. So why is that? It's because the smart antenna technology allows devices on each access point to transmit at the same time without causing interference. That smart antenna is basically able to ignore the noise coming from the client talking to the other AP. The other important thing to note here is, look, the throughput between each of those APs is about the same. You look at Ubiquity, one AP is hogging up the bulk of the airtime, getting nearly double the throughput of the other AP. So now we turn on a third AP, and what happens? Our aggregated throughput continues to grow, and we've gone from 133% utilization of airtime, versus Ubiquiti, where their airtime utilization actually dropped to 91%. So why did Ubiquiti's drop from 95 to 91? And it's, again, it comes down to basically just how efficiently they're using that airtime. We've now got more devices all trying to take turns using the airtime, and they're end up using it much less efficiently because of the way Wi-Fi works with it, backing off when it detects someone else transmitting. You'll also notice, again, when it comes to bandwidth per AP, it's very evenly distributed versus Ubiquiti, where it's highly unevenly distributed, because basically everything's causing interference with everything else, where with ours, the smart antenna allows us to better utilize the airtime and theoretically achieve more than what's supposed to be available. So now just some general rules of thumb when it comes to installing stuff here for you. Again, we talked about before, a traditional access point is designed to be mounted on a ceiling. It's got this round sort of circular coverage pattern. But a lot of times, for whatever reason, you end up mounting that on the wall instead of on the ceiling. So it gives you really poor performance when you do that. The bulk of the signal is going into the floor and ceiling, and it doesn't get the sort of horizontal penetration that you would generally want. On the Zyxel side of things, smart antenna helps solve that. Some of the antenna patterns we can use will help work better. We also have a number of APs which have something called a dual optimized antenna. So instead of having one antenna, we've got two different sets of antennas. One that's optimized for ceiling, one that's optimized for wall mount. And you can switch between them based on where you install the access point. So just in general, you want to mount your access points in the ceiling, generally in a central location over the areas that they're trying to cover. You're trying to minimize the distance between the client device and the AP, and also minimize the amount of obstructions the signal has to go through. So if you mount it higher up, it's easier for that signal to bypass cubicle walls, bypass other humans, things like that. So generally, the higher the access point, the better. Not necessarily the case in situations where you've got a lot of APs in a small area like a conference room or an expo hall or something like that. But in general, in a typical office install, that's what you want to try to do. So one thing here that people always get upset sort of about is, hey, I want to mount this access point onto the drop ceiling, and we do have clips and things like that that allow you to clip it on, but you still have to run the Ethernet. People don't like to drill holes in the drop ceiling to run the cable. It's kind of hard sometimes to hide those cables and things like that. So just in general, you don't need to mount it onto the drop ceiling. Just set it on top of the drop ceiling. And you would want the logo facing down, not like what it shows here in the graphic. Just like you would as if you were mounting it directly to the drop ceiling. Very little attenuation from the drop ceiling materials. So oftentimes it's just easier, just lay it on top of the drop ceiling if code allows you to, and you should be fine. If you're mounting it up onto the physical ceiling above the drop ceiling, keep in mind there's generally a lot of metal up there, right? There's, there's all the wires that are holding the drop ceiling in place. There's oftentimes all sorts of ductwork and pipes and things like that, conduit. So just keep in mind all those metal things are going to cause problems both with attenuation of the signal and also increasing some of the noise and reflections and things like that. So oftentimes you don't want to mount it directly onto the real ceiling because of that. So for hotels, the traditional way of doing this was you would put an access point in the hall. It would cover anywhere from 4 to 16 rooms. So what you're seeing now is more and more hotels are getting to a 1 AP per room policy or a 1 AP per every other room. So why are we doing that? And it just has to do with how people are using Wi-Fi has changed a lot over the years. Traditionally, not every hotel guest would have a wireless device. Those that did were probably just downloading their emails for work, things like that. But now, everybody's got multiple Wi-Fi devices. You've got your Kindle Fire, you've got your Kindle tablet, you've got your iPad, you've got your cell phone, you've got your laptop. If there's multiple people in your party, each of them probably has 2 or more devices. So what happens is you've got issues with just not enough bandwidth per AP for all the users. and devices. Instead of just downloading email, people are wanting to stream YouTube and Netflix. And then the other thing just comes down to signal strength, right? You know, that cheap $49 Walmart tablet doesn't have a lot of output power to get that signal back out to the access point in the hall. So that's why you're seeing more and more switch to this one AP per room. So some things to keep in mind is you want some sort of locking mechanism if you're mounting these APs in the rooms. Most of our APs don't have a true lock, but figuring out how to release the AP from the mounting bracket generally is something no one's going to figure out easily on their own. And needs a screwdriver or chopstick or something to hit that release. You also want to make sure to turn off the LEDs if you're mounting these in the room. You know, it's hard to sleep when you've got flashing green lights above your head. When it comes into public areas, the main thing you want to look at is user density. How many users are going to be using the internet at a time? Are there really going to be a lot of people connecting to the bar Wi-Fi or the lobby Wi-Fi, you know, versus say a conference room where you may have 30 or 40 people all trying to connect at once? Use load balancing and client steering in these public areas to help sort of ease the load. And plan your coverage based on the physical location. Lobbies should be separate from the coffee shop, should be separate from the pool. Anywhere where you're going to have a lot of devices on there, use smart antenna. Smart antenna makes a huge difference in conference rooms and expo centers and convention halls and things like that. For schools, the thing to keep in mind again is how many users are you going to have? How many students are going to be connected? Is this a classroom where you know, maybe a few people will get online at the end of the day to do some studying? Or is this a smart classroom where the teacher is streaming video to each student's laptop? Every student is connected with a Chromebook or an iPad. Those are some questions you need to ask. Just as a general rule, some things here is, you know, teachers and students should be on different networks. They should be VLANed off from each other with some exceptions, you know, what's the term I'm looking for here? Some exceptions put into the rules to allow teachers to push content if you are pushing content in the classes. Generally, as soon as you get 20 or more students, you should have at least 2 access points. Again, guys, send in the questions if you can with the Q&A, because that's the one I can see. While we're presenting here, I can see it flashing that somebody sent me a chat. I will get to it at the end. So generally, if you have 20 students, you'll want 2 APs or more per classroom. Whether we're talking Nebula or controller-based stuff, we have a special smart classroom mode on all of our APs with some algorithms that are specifically optimized for a classroom where you have, you know, 20, 30, 40 students all connecting simultaneously to the network. And if you have 30 or more students, or you have a smart classroom where you're streaming video to everybody simultaneously, smart antenna is the way to go. Almost done, guys. So I'm going to talk a little bit here at the end with 802.11ax, AK Wi-Fi 6, AK high efficiency wireless. So 11ax or Wi-Fi 6 is really cool. They've done a lot of things here where they've essentially rewritten how Wi-Fi works, solving a lot of the issues we talked about earlier in today's presentation. So unlike 11AC, Wi-Fi 6 works in both 2.4 and 5 gigahertz. So 2.4 devices are going to see benefits also, unlike 11AC where it was only 5 megahertz devices that could take advantage of the changes. It's specifically designed to deal with interference from other devices and to handle lots of users connected to the same access point. So some of the things we've done here is we've added higher we have what's called OFDMA, which allows the access point to basically coordinate and tell clients when it's their turn to talk. So instead of having you know, every device fighting for themselves, waiting for an opening to be able to shout their whatever data they want to send, the access point now has the ability to control that and assign and allot amounts of bandwidth for people. We have MIMO now is able to work upstream to the access point instead of downstream only. We have what's called spatial frequency reuse, a number of other really cool technologies. The funny thing with this is the IEEE group isn't expected to actually ratify the standard until September 2020. So everything that's 11AX is based on the draft. Most of the newer products will be able to support everything. The older stuff, some of the older so-called Wi-Fi 6 APs will never be able to get all the features. The silicon itself doesn't support what's going to happen in the final version of the spec. So here's an example. When it comes to Wi-Fi 6, there's two major Wi-Fi chipsets. There is the Qualcomm and Broadcom. And I've got the Qualcomm chart up here. The Broadcom chart is very similar. Basically, the Gen 2 stuff didn't start shipping until August or September of this year. So if your Wi-Fi 6 access point launched in July, or launched in January, or launched the year before in 2018, it's using a Gen 1 chipset. So what does that mean for you? It means there's a lot of these really cool features that are part of Wi-Fi 6 that are not and never will be supported on that older chipset. So you don't get the OFDMA, the upstream OFDMA. You're not going to get your upstream MIMO. You're not going to get TWT. You're not going to get BSS color coding. And nobody is advertising and telling you what chipset is in there. They're just going to call their product Wi-Fi 6. So that's something to keep in mind. Look at when the product launched. And that's probably a really good rule of thumb of whether it's using Gen 1 or Gen 2. If you're trying to future-proof your network, you want to use Gen 2, whether we're talking a Qualcomm-based product or a Broadcom-based product. So for Zyxel, our business access points, all of our Wi-Fi 6 access points are using Qualcomm Gen 2. We do not have any business class products that will be using the Gen 1 chipsets. Now, having said that, even though it's Gen 2, a lot of these features aren't available today, but they will be available as a firmware upgrade later. As we mentioned on the last slide, the actual specs are not fully approved. So some of these features will get added later this summer as the drafts become more fleshed out and Qualcomm has more time to work on the drivers and code. Some of the features may not come out until Q4 of this year, just because they're waiting for the spec to be 100% fully ratified before it's implemented. So that's also something to keep in mind. So again, Gen 1 chips, whether Broadcom or Qualcomm, are going to be missing some features that they're never going to get. So try to buy Gen 2, because that's going to be where you're eventually going to have all of the Wi-Fi 6 features. So with that, we take it to Q&A. And I'll start answering some questions here for you guys. Again, send them in using the Q&A box if you can. Some other stuff to draw your attention to here is a lot of people don't realize it, but we do have a forum. We have a user forum, forum.zyxel.com. You can go to, talk to your other Zyxel users, but more importantly, unlike most of the other user forums out there, ours is actually read by our engineers and R&D and some of our support staff in CSO, Taiwan. So know when you post something on there, whether it's feedback or a question, someone from our headquarters is going to see it, and oftentimes they will respond to you there. So if you've got some comments or feedback that are not high priority, you can just post them there, get feedback from your other users and feedback there. And then my email's on there too. So feel free to email me with feedback, offline questions, whatever ideas you have. So let's start going through some of these questions. So this is from Craig Pittman. In Nebula, I only see a setting to turn off LEDs for all APs. Is there a way to pick and choose which APs will have the LEDs on for a site? I don't think there is. There may be a way to do it using tags, right? We have the ability to tag APs and then implement some things per tag. Go ahead and just send me an email. Again, it's on the screen there, but Shawnr, S-H-A-W-N-R @zyxel.com. Send me an email, and I will look into it and get you the official answer. But I think it is no. I think it's all or nothing at the moment. But I can double check that and see if maybe there's a way to do it using the tag function. Paul Cook is asking, is there Wi-Fi 7 in the works? Eventually, at some point, there will be a Wi-Fi 7. I'm sure there's probably already an IEEE working group that's started the process. But you're talking, my guess, just from what I've seen, is we're probably minimum 5 years out, very possibly a lot more than that before you come up with something like that. So Wi-Fi 6 is going to be around for a while, and it's going to be the standard going forward. You do need Wi-Fi 6 clients. This is something else I should have probably mentioned on the other slides. But in order to get all these features, not only does the access point chipset have to support it, not only do the drivers on the access point have to support it, the client devices also have to support a number of these features. Right, so in general, client devices lag behind the access points by at least a year. So while you've got Apple and Samsung shipping products that they claim are Wi-Fi 6, it's a very limited subset of those Wi-Fi 6 features, and they probably all won't be there for quite a while. I mean, they're not all there now on the access points. They're not going to be all there on the clients for some time. So that's something else to keep in mind, but there are still benefits of going Wi-Fi 6 now. There are some benefits you will see with legacy clients, and as more and more of your devices are using Wi-Fi 6, they're using the RF spectrum much more efficiently, which means they're freeing up additional airtime for those legacy devices. The legacy devices will still see some benefits as time goes on and more devices are supporting Wi-Fi 6 on the client side of things. I am not seeing any more questions, which is amazing to me. So if you have something you're typing up right now, go ahead and pause, highlight it, copy it, and go ahead and send me an email directly. Again, it's seanr@zyxel.com, and I'll take those questions offline. But I appreciate everybody turning out today. If you have any ideas for topics and subjects you'd like to see us cover, let us know. We want these presentations to be valuable for you. So let us know what is and is not working for you. And if you have any ideas for topics you'd like to see us cover, whether it's me or Troy or Marcus, feel free to email me or email your salesperson and let them know. Thanks, everybody.